This is a lecture on colors. No, I didn't misspell color or colors. This is the British way of spelling it, the original way to spell it in English before Merriam-Webster changed it due to some strange patriotism. Roy G. Biv, I wanted 7 letters. The objectives describe what happens when sunlight is passed through a triangular shaped prism. Describe how the reflection of light affects an object's color. Describe what determines whether a material reflects, transmits, or absorbs light of a color. Describe white light. State the 3 colors that can be combined to form almost any color. Define complementary color. Describe color mixing by subtraction. Explain why the sky is blue, why sunsets are red, and why water is greenish blue. Explain how atoms emit light. Like the former chapter, these are the basic objectives. There's a lot more to learn in this chapter than might be prescribed by these particular objectives. So let's begin right away. Newton passed sunlight through a glass prism to form the color spectrum. He actually used information written by a fellow by the name of Alhazen, which we will get to in a moment. If I take a stack of razor blades and you see that the sharp part of the razor blade is dark, when a stack of razor blades bolted together is viewed end on, the edges appear black. Light that enters the wedge-shaped spaces between the razor blades is reflected so many times that most of it is absorbed. When light's absorbed, no light reflects and it's dark. This is a picture of an old girlfriend of mine who's putting on red lipstick under fluorescent light, and when she gets in the sun it looks magenta. So it depends on the type of light that's being reflected. Not all light is the same. Here's a picture of the fellow Alhazen, the polymath having learned much, sometimes if male, referred to as a Renaissance man. Alhazen was born in Basra in the Iraq province of the Umayyad Empire. He probably died in Cairo, Egypt during the Islamic Golden Age. Basra was a key beginning of learning, and he was educated there, and in Baghdad, the capital of the Abbasid Caliphate and the focus of the high point of the Islamic civilization. That's going back around the 9th century, 10th century. During his time in Bayad, Iran, he worked as a civil servant and read many theological and scientific books. One account of his career has him called to Egypt by Al-Hakim bi Amr Allah, ruler of Fatima Caliphate, to regulate the flood of the Nile, a task requiring an early attempt at building a dam at the present-day site of the Aswan Dam. After deciding the scheme was impractical and fearing the Caliph's anger, he feigned madness. He was kept under house arrest from 1011 until Al-Hakim's death in 1021. During this time, he wrote his influential Book of Optics. He is the father of optics. After his house arrest ended, he wrote scores of other treatises on physics, astronomy, and mathematics. He later traveled to Islamic Spain. During this period, he had ample time for his scientific pursuits, which included optics, mathematics, physics, medicine, and practical experiments. Again, Alhazen is the father of optics. We spend a lot of the material we know today of optics comes from his early writings. This square absorbs all the color illuminating it. In sunlight, it is warmer than the white square because of the absorption of all color. That's why black is warmer, because it absorbs all color, all light. This square reflects all the colors illuminating it, so it's not going to warm as much. In sunlight, it is white. When illuminated with blue light, it's blue. When illuminated with red light, it's red, etc. Different materials have different natural frequencies for absorbing and emitting radiation. In one material, electrons oscillate readily at certain frequencies. In other material, they oscillate readily at different frequencies. At the resonant frequencies where the amplitudes of oscillation are large, light is absorbed. Recall from the previous chapter that glass absorbs ultraviolet light for this reason. But at frequencies below and above the resonant frequencies, light is re-emitted. If the material is transparent, the re-emitted light passes through it. If the material is opaque, the light passes back into the medium from which it came. This is reflection. You might want to put this on pause and read this again. A very important aspect of this particular chapter on color. When red light shines on a red rose, why do the leaves become warmer than the petals? When red light shines on a red rose, why do the leaves become warmer than the petals? Well, think about it. Remember, what color are the petals? The petals are red. So the leaves absorb rather than reflect the red light. So the leaves become warmer. It reflects green light, the leaves. But the rose, you can see, is red, so it reflects it, doesn't absorb it. When green light shines on a red rose, why do the petals look black? When green light shines on a red rose, why do the petals look black? Well, think about it. The petals are red and you're shining green light on it. Is the green light going to reflect back? No, the petals absorb rather than reflect the green light. So the rose appears to have no color at all, black, because everything is being radiated, is being absorbed. So remember, when you see something, you are seeing the color that is reflected from that object. If there's no light, for instance, if you're in a dark room and there's no light, the color is black. You only have color if you can have reflected light. Blue glass transmits all energy of the frequency of blue light. Energy of the other frequencies is absorbed and warms the glass. So I'll have white light shining on a blue glass. Well, Roy G. Iv will be absorbed by the glass. The glass will get warmer. But the blue glass is blue because only blue light passes through the glass. This is a radiation curve of sunlight in a graph. Is a graph of brightness versus frequency. Sunlight is brightest in the yellow-green region, in the middle of the visible range. Very, very, very important graph to understand. Very important graph. And you can see that red is a little bit dominant, but violet is not. Yellow-green light is the brightest part of sunlight. Since humans evolved in the presence of sunlight, it is not surprising that we are most sensitive to yellow-green. That is why it is more and more common for new fire engines to be painted yellow-green, particularly at airports where visibility is vital. This also explains why at night we're able to see better under the illumination of yellow sodium vapor lamps than we are under tungsten lamps of the same brightness. The blue portion of sunlight is not as bright, and the violet portion is even less bright. That's why the sky is blue. The graphical distribution of brightness versus frequency in the figure on the preceding page is called a radiation curve of sunlight. Most whites produced from reflected light have this frequency distribution. Here's a picture. I'm going to show you some pictures of green, some mid-green. This is actually kind of like chartreuse. Here's a fire engine. Here's a vest. I used to wear this kind of vest when I was on the parkway on EMT calls. Here's a picture of an old horse I used to have. He was green. I called him simply Chartreuse, that was the name of my horse, Chartreuse. Put a saddle on Chartreuse, and he was very happy. Now, there's different shades of Chartreuse as well. I have green Chartreuse, yellow Chartreuse, pear is kind of a Chartreuse, yellow-green, green-yellow. So different various shades of Chartreuse. Tennis balls have a color of Chartreuse. Golf balls will have a color of Chartreuse. So you can see them. Again, our eyes evolved in the presence of Chartreuse. Artists use both creativity and science to paint. By mixing pigments in just the right proportions, an artist can produce all of the colors necessary to capture an image. To artists, mixing colors can be a matter of trial and error. They add colors until they achieve the desired color. As they do so, they are using the process of color mixing by subtraction. Some artists work independently, selling their works to interested buyers. Others are employed to create images for books, movies, or advertisements. Some extra credit. Find a sub at the school who knows all about color and ask him or her to come in and give a discussion, brief discussion on color pigments, color of pigments. Okay, here is light. Here is light. You have three primary colors of light: blue, red, and green, and they add in the following ways. Okay, so for instance, red and blue is magenta, red and green is yellow, and green and blue is cyan, and then all three colors add to white. So addition is involved with light. Production of secondary colors of light by adding primary colors of light. The low frequency, middle frequency, and high frequency parts of white light appear red, green, and blue to the human eye. So the secondary colors are red and green is yellow, and then red and blue is magenta, and then green and blue are cyan. So yellow, magenta, and cyan are called secondary colors of light and the red, green, and blue are primary colors of light. Now, this is not to be mistaken with primary colors of paints. Paints are very different. Things are very different when it comes to pigments. Don't confuse the two. What color does red light plus blue light make? What color does red light plus blue light make? If you look at the color discs, those three round discs that were joined together, you'll see that it makes magenta. Magenta is the color that red and blue light makes, not pigments, but light. Here is the figure I was speaking of. It's visible light. Its color through addition. This can be understood if the frequencies of white light are divided into three regions as shown in the figure on the preceding page. The lower frequency red end, the middle frequency green part, and the higher frequency blue end. The low and middle frequencies combined appear yellow to the human eye. The middle and high frequencies combined appear greenish blue or cyan. The low and high frequencies combine to form the bluish red magenta. You can make almost any color at all by overlapping red, green, and blue light and adjusting the brightness of each color of light. This amazing phenomenon is due to the way the human eye works. The three colors do not have to be red, green, and blue, although these three produce the highest number of different colors. For this reason, red, green, and blue are also called the additive primary colors. Red, green, and blue are called the additive primary colors. Here is a picture of a stage star here under the three lights and all the colors that exist as a result of that. This is 3 lights in a television. The old style television are red, green, and blue. This is another example of that. That blue might be a little light for blue, but anyway, the old cathode picture ray tubes, they're 3 colored beams, a red, green, and blue. What happens when 2 of the 3 additive primary colors are combined? When 2 colors are added together to produce white, they are called complementary colors. For example, we see that yellow and blue are complementary to yellow. After all, is the combination of red and green. And red and green and blue light together appear white. By similar reasoning, we see that the magenta and green are complementary colors, and cyan and red, as are cyan and red. Every color has some complementary color that, when added to it, will produce white. So, complementary colors, very, very important. And I'll show you that in the next slide. Here we have addition of light, etc. Now a little thought on the inspection of the figure will show that when we add in a third color, we get white. And that third color is the complementary color. So you can see from the drawing, if you inspect the drawing and the complementary chart, you'll be able to understand a little bit. And here is a summary of addition of light. Red and green make blue. Red, green, and blue make white. Red and green, and then add yellow and blue, and that's white. Red and blue and magenta, add green and it's white, etc. So you can get all of this information from that tricolor red, green, and blue. What color does white light minus yellow light appear? And what color does white light minus green light appear? Again, you can get the answer to this by looking at the tricolor discs that I showed you several pictures ago. It says, what color does white light minus yellow light appear? So if I take the yellow out of it, what am I left with? And that's obvious. And what color does white light minus the green, if I take green out of it, what does that color appear to be? So if I take the yellow out of it, I'm left with blue, and I take the green out of it, I'm left with magenta. Is that right? So make sure that reasoning is correct. Make sure you can answer these questions. These will be questions similar to questions that are on the test. What color does white light minus yellow light appear to be? What color does white light minus green light appear to be? And again, this is by subtraction, actually, is what we're starting to get into. So the answers to this are, as I suspected, blue and magenta. So you may want to go back and qualify that. So what we're starting to get into now is we're using the additive color discs, and we're talking about subtraction of color. Now, if you begin with white light and subtract some color from it, the resulting color will appear as the complement of the one subtracted. Not all the light incident upon an object is reflected. Some is absorbed. So now we're going to get a little bit into the subtraction, color subtraction, and that's going to be true with pigments. The part that is absorbed is in effect subtracted. So it's going to be color by absorption. It's subtracted from the incident light. For example, if white light falls on a pigment that absorbs red light, the light reflected appears cyan. A pigment that absorbs blue light will appear yellow. Similarly, a pigment that absorbs yellow light will appear blue. Whenever you subtract a color from white light, you end up with the complementary colors. Well, one of the main reasons you have to talk about, even though you're talking about pigments, you have to talk about light, is because any pigment is black unless you have light. So it all begins with light. Let me say it again. Any pigment is black unless you have light. Light is the only thing that gives pigment its color. Artists know that if we mix red and green and blue paint, the result will not be white, but a muddy, dark brown. Red and green paints certainly do not combine to form yellow as red and green light do. The mixing of paints and dyes is an entirely different process from the mixing of colored lights. But you still have to talk about light again. You still have to talk about light when you talk about pigments, but it's very different. Paints and dyes contain finely divided solid particles of pigment that produce their colors by absorbing light of certain frequencies and reflecting color of other frequencies. Pigments absorb light of a relatively wide range of frequencies and reflect a wide range as well. In this sense, pigments reflect a mixture of colors. When paints or dyes are mixed, the mixture absorbs all the frequencies each paint or dye in it absorbs. So again, when you're talking about color of pigments, it's going to be different than addition, but you still have to keep into account that it's light that gives the pigments its color, not the pigment itself. The pigment will absorb certain colors and thereby subtract certain things. For instance, the blue paint, for example, reflects mostly blue light, but also violet and green. It absorbs red, orange, and yellow light. So the pigment can reflect a variety of colors to give those shades, those pigment shades. So this pigment is going to reflect the higher energy waves and absorb the lower energy waves, such as red, orange, and yellow. Now, if I have a yellow pigment or yellowish pigment, it's going to reflect red, orange, yellow, and green, and you get this funky kind of yellow color, as opposed to it's going to absorb the higher energy waves. So you're subtracting out the blue and the violet, or the blue and the indigo. You're subtracting those colors out. So when you talk about coloring by, or the combination of colors, or the formation of a color by subtraction, it's not so much subtraction as what colors are being absorbed or subtracted out by absorption. When blue and yellow paints are mixed, then between them they absorb all the colors except green. As the three figures show, pigments reflect is green, which is why the mixture looks green. You're absorbing red, yellow, orange, blue, indigo, violet here, and you're reflecting the green light. Don't forget, in here, this process is called color mixing by subtraction, or you could say color mixing by absorption, to distinguish it by the effect of mixing colored light, which is called mixing color by addition. Just want to make sure you understand what indigo is. Roy G. Biv, I for indigo. It's navy blue. So jeans that aren't faded, that dark blue, that's actually indigo. Nobody likes the name indigo, so they call it navy blue, but it's actually indigo. Here's color by subtraction. The pigment is red, so it absorbs blue-green and reflects red. The pigment color and the reflected color are actually the same thing. Green is going to absorb blue and red, So green will be reflected, blue will absorb red and green. So blue is affected. Yellow is actually red and green together. So that's kind of like, this is kind of like subtraction and addition, because yellow is actually red and green light, and cyan is green and blue light, and magenta is red and blue light. But what's being absorbed is going to be blue, green, blue, red, red, green, blue, red, and green as you go down the middle column. So again, that's color by subtraction. So when you cast lights on a stage at the school play, you use the rules of color addition to produce various colors. But when you mix paint, you use the rules of color subtraction. You may have learned as a child that you can make any color with paints of three so-called primary colors: red, yellow, and blue. Actually, the three paint or dye colors that are most useful in color mixing by subtraction are magenta, blue-red, yellow, and cyan, greenish-blue. Magenta, yellow, and cyan are the subtractive primary colors used in printing, as opposed to the additive primary colors red, blue, and green. Now, if I took a color, or here's a vent, some kind of thingamajig, whatever it is. Anyway, I look at the colors very closely. I really have no idea what that is a picture of. Anyway, found it on the internet. Anyway, if I looked at the color closely of a printed picture, this is a picture that's printed on an inkjet printer, and the color is made of the three subtractive colors relative to pigments: magenta, yellow, and cyan, as well as the black. So here is a microscopic look at that little section of the printed page, and I'll show you that in class. It's actually quite interesting, where it's a matrix, literally a dot matrix of the different colors. Color printing is done on a press that prints each page with 4 different colored inks, like I just said: magenta, yellow, cyan, and then the final black, which gives it kind of a nice outline in succession. Each color of ink comes from a different plate, or ink cartridge, which transfers the ink to the paper. The ink deposits are regulated on different parts of the plate by tiny dots. Examine the color plates in this book or in any magazine with a magnifying glass and see how the overlapping dots of 3 colors plus black give the appearance of the actual picture. So it's these dots that are going to combine to form the picture. If I had a picture of 4 kids at a birthday party, and just used magenta, it would look like A. Just yellow, it would look like B. Cyan, C. Now, if I mixed all of the magenta, yellow, and cyan, I wouldn't have any of the shadows, nothing to kind of like make it crisp. So E is just the black and white. So if I take the black and white, if I take E to D, it gives it that crispness where I can see individual boundaries. So black is very important to give the other colors borders, boundaries. It brings out the crispness. We talked about umbra. It gives it kind of like an umbra look, where you don't have that diffusion where one color is diffusing into another. You have the black, which acts sort of like a border between the two. A beam of light falls on an atom and causes the electrons in the atom to move temporarily in larger orbits. The more vigorously oscillating electrons re-emit light in various directions. Light is scattered. It's going to be important when we talk about why the sky is blue. Most of the ultraviolet light from the sun is absorbed by a protective layer of ozone gas in the upper atmosphere. The remaining ultraviolet sunlight passes through the atmosphere, is scattered by atmospheric particles and molecules. The sky is blue because its component particles scatter high-frequency light. Of the visible frequencies, violet light is scattered the most, followed by blue, green, yellow, orange, and red in that order. Red light is scattered only a tenth as much as violet. Although violet light is scattered more than blue, our eyes are not very sensitive to violet light. Our eyes are more sensitive to blue. So we see a blue sky, not a violet sky. Amazing. Skies are actually violet. Okay. Here's a picture of the sky, blue. Even this sky has variations in the blue family. It's not just one color of blue. A blue jay, there are no pigments, no blue pigments in the feathers of a blue jay. Instead, there are tiny alveolar cells in the barbs of its feathers that scatter light, mainly high-frequency light. So a blue jay is blue for the same reason the sky is blue. Scattering. The scattering of light. Why sunsets are red. The lower frequencies of light are scattered the least by nitrogen and oxygen molecules. Therefore, red, orange, and yellow light are transmitted through the atmosphere more readily than violet and blue. Red light, which is scattered the least, passes through more atmosphere without interacting with matter than light of any other color. Therefore, when light passes through a thick atmosphere, light of the lower frequencies is transmitted while light of the higher frequencies is scattered. At dawn and at sunset, sunlight reaches us through a longer path through the atmosphere than at noon. Here's an example. By the time a beam of sunlight gets to the ground at sunset, only the lower frequencies survive, producing a red sunset. Greatest path of sunlight through atmosphere is at sunset or sunrise. You can see here that the shortest path is at noon, and the thickest, or the thickest layer is in the early morning or in the evening. If molecules in the sky scattered low-frequency light more than high-frequency light, how would the colors of the sky and sunsets appear? If low frequencies were scattered more, red light would be scattered out of the sunlight on its long path through the atmosphere at sunset, and the sunlight to reach your eye would be predominantly blue and violet. Would be predominantly blue and violet. Distant dark mountains are bluish in color. What is the source of this blueness? The hint is what is between you and the mountains you see. So why are the mountains bluish when they have green trees on them? Well, if you look at distant dark mountains, very little light from them reaches you, and the blueness of the atmosphere between you and the mountains predominates. The blueness is of the low altitude sky between you and the mountains. The blueness is of the low altitude sky between you and the mountains. What I'll do is I'm going to put up a couple of pictures of sunset, gorgeous sunset in the tropics or wherever. You get this beautiful beautiful range of long wavelength light, the low frequency light, the red, orange, yellow hues that are so dominant in sunsets. Distant snow-covered mountains reflect a lot of light and are bright, but they sometimes look yellowish depending on how far away they are. Why are they yellowish? Hint, what happens to the reflected light as it travels from the mountains to you? Interesting. Well, the reason is distant snow-covered mountains often appear a pale yellow because the blue in the white light from the snowy mountains is scattered on its way to you. The complementary color left is yellow. I tried to find some pictures, but the pictures are always white balanced, so you don't see that yellow picture, that yellow hue from the broad daylight. Here is water. Water appears blue. Most people think that water is blue because of the sky. Water is transparent to nearly all visible frequencies of light. Water molecules absorb infrared waves because they resonate in the frequencies of infrared. The energy of the infrared waves is transformed into kinetic energy of the water molecules. Infrared is a strong component of the sunlight that warms water. Water molecules resonate somewhat to the visible red frequencies. Resonates. In other words, it's going to absorb the red. This causes a gradual absorption of red light by the water. A 15-meter layer of water reduces red light to a quarter of its initial brightness. There is very little red light in the sunlight that penetrates below 30 meters of water. When red is taken away from the white light, what color remains? This question can be asked in another way. What is the complementary color of red? And the answer is cyan. Blue and green are left over, and blue and green make up cyan. The complementary color of red is cyan, a greenish blue color. In seawater, the color of everything at these depths looks greenish blue. And don't forget, it's a kind of a round trip. I'll go over that a little bit in class. But those are true colors, and that's not because of the sky. That's because of it absorbing those colors. Many crabs and other sea animals that appear black in deep water are found to be red when they are raised to the surface at great depths. Black and red looks the same. So both black and red sea animals are hardly seen by predators and prey in deep water. They have survived an evolutionary history while more visible varieties have not. Here I have the different electron orbits in an atom are like steps in energy levels. When an electron is raised, that was A, this is B. When an electron is raised to a higher level, the atom is excited. When the electron returns to its original level, it releases energy in the form of light. You remember the flame test with chemicals, like, for instance, strontium was red. I blow it full of energy. I excite everything with this random energy of a flame, and it goes into higher orbits. But then when it falls back down and gives off these packets of energy, those are organized. Those are specific wavelengths that are consistent to that particular element, and those are red wavelengths that are given off for strontium. So strontium, when it's excited, gives off a red color. Here I have another example of something exciting the electron, and then the electron gives off energy. That's the third one. Left, right, then bottom left. The energy is being given off in the form of a photon, electromagnetic radiation. So that's what this is all about, actually. These few slides are about electromagnetic radiation. It's a great example of absorption and emission. You have an electron that absorbs energy. It goes from the second energy level to the third, and then it goes back down from the third to the second, and that's emission. So you have absorption, excitation, and then emission. You have light broken down into its component parts, visible light being broken down into component parts with those are convex lenses, a prism, and a mirror. A fairly pure spectrum is produced by passing white light through a thin slit, two lenses, and a prism. Here's a rainbow where water molecules, water particles in the air are refracting the light, bending it, separating it into its component parts. Here's a spectroscope. A spectroscope separates light into its constituent frequencies. Light illuminates the thin slit at the left, and then it is focused by lenses onto either a diffraction grating shown or a prism on the rotating table in the middle. Here are some spectrographs. This is an incandescent bulb that shows pretty much all of them: red, orange, yellow, green, blue, indigo, violet. There are probably some missing, but they're so subtle. Hydrogen is broken down into these particular component parts. Sodium is mainly that orange color, etc. Here's a picture of the eye. You have the conjunctiva, conjunctive formed with conjunctivitis, just below the, it forms below the bottom lid or the upper lid, the conjunctiva. You have the cornea, the lower lid. There's the skull above, the upper lid, etc. The next one is a little bit more involved, where you have the different blood vessels, the central retinal vein and the central retinal artery. And then you have blood vessels, the vitreous body. You have a variety of other things. All right, so that's it. Good luck. Take notes. Give them to me after your quiz, chapter quiz, and goodbye.